Hello everyone. In this video, we will do some examples for trig substitution x equal to a constant times sine theta. Well, this substitution works when you have square root of a constant square minus x squared in your integral. Then if you apply, the whole point of this substitution is that your square will turn to a squared minus a square of sine squared theta. Then you just factor out a squared, and 1 minus sine squared is same thing as cosine squared theta. And well, that is how the substitution helps us to get rid of that square root. Let's see this in some practice, okay? The first example, we have 9 minus x squared. So in this case, a is basically 3. 3 squared is 9. So let's use x equal to 3 sine theta. You can actually use 3 times cosine theta as well. But in either case, changing the integral to new variable integral is not difficult because it just goes smoothly. Let me show you here. Unlike the other substitutions, in trig substitution, changing is easy. Just 3 squared is 9 sine squared theta. 9 minus 9 sine squared theta. And then there will be, for dx, we have this whole thing to replace. And now we can do some trig simplification inside, and you notice that there will be constant 81. This piece here will turn to 3 cosine theta, and then that will give us. So that's another good thing for the trig substitutions. It changes the integral to a trig integral that we already know how to deal with. So in this case, we need to use the power reduction formula for sine and cosine, or basically half angle formulas. Yes, so this will be half of 1 minus cosine 2 theta, and the other one half of 1 plus cosine 2 theta d theta. Let us put those constants outside. 1 minus cosine 2 theta times 1 plus cosine 2 theta. This will give me 1 minus cosine squared 2 theta. So we have again even powers. We can apply the half angle formula another time. So this time we will get 1 plus cosine double of the angle, which will be 4 theta. Okay. Now let's see what we have here. 81 over 4. That will actually give us half minus half of, so I can put that half out, and I get 1 minus cosine of 4 theta. Now this is just an easy integral. You need to use substitution, or just the integral of cosine 4 theta is 1 over 4 sine 4 theta. So this will give me theta minus 1 over 4 sine 4 theta. As you know, as we had in all other substitutions, the substitution is not complete unless you put back in your original x. So here, to be able to put back in that x, I will need some more simplification on the last term. So here what we have is 81 over 8 theta minus. Remember, I am using this double angle formula, sine of 2 theta, or let me just now write 2 alpha is 2 sine alpha cosine alpha, and cosine of 2 alpha is cosine squared alpha minus sine squared alpha. Or I could use 1 minus 2 sine squared. So in this case, that means that if I apply once, I will get 81 over 8. So there will be, okay, let me put that 4 out there. There will be 2 sine of 2 theta cosine 2 theta. And then another time you apply that, this will give us 81. Well, yes, so this will be 16. 2 sine theta cosine theta for the first one, and for the second one we will have 1 minus 2 sine squared theta. Yeah. Now that everything is in terms of theta, you know that, well, x over 3 is equal to sine theta. From there, you can see that theta is going to be sine inverse of x over 3. So that will give me 81 over 8 sine inverse of x over 3 for the first term. For the second term, by the way, this will cancel there. So we will get minus 81 over 8, and this will be sine of well, sine theta itself here is equal to x over 3, and cosine of theta, well, you can use either cosine theta as root 1 minus sine square, or use the reference angle. So this guy is theta, this is x, this is 3, this will be 9 minus x squared. So that will give me cosine theta is 9 minus x squared over 3. Then 1 minus sine theta is x over 3, square that, so that is what we have there. Okay, plus c. Well, I can continue now and finish this, what we had here. So sine inverse of x over 3 minus, okay, so now if I find the common denominator, there will be 81 in the denominator. So this will be 1 over 8 x, 9 minus x squared. And then here it will be 9 minus 2x squared plus c. So we turn back everything successfully to x integral. Okay, so let's do another example here. 12 minus 3x squared. The first thing you notice here is that, okay, I don't have a square minus x squared. But if you do one step here, so let me do it right up here. If you factor the coefficient of x squared, so it will be 3 4 minus x squared over x squared dx. In that case, well, I can factor, well, take out that root 3, and now you see that I have 4 minus x squared over x squared dx. And well, from there you notice that the substitution we can use here is x equal to 2 sine theta. As I said, you can use 2 cosine theta as well. Well, obviously then dx is going to be 2 cosine theta d theta. And since this is definite integral, we have to go and change the x boundaries to theta boundaries. So x is equal to 1, x is equal to 2. If x is equal to 1, then I have 1 equal to 2 sine theta, and that means that theta is going to be, well, what is the angle whose sine is half? That's pi over 6. We are finding the theta in the domain of sine inverse, or in the in the range of sine inverse, or in the domain of sine which defines sine inverse. Okay, so for this other one as well, we can find theta is equal to pi over 2. So my integral 1 to 12 3x squared over x squared dx now turns to root 3 integral from pi over 6 to pi over 2. Here I have root of 4 minus 4 sine squared theta over, in the denominator we have 4 sine squared theta, and dx is 2 cosine theta d theta. Okay, now do the substitution here. Well, simplification. So the numerator will give us another 2 cosine theta. So this will be 4 cosine squared theta over 4 sine squared theta d theta, which is okay. So we are in now good shape, because this is a simple integral. This is cotan squared theta d theta. Okay, well, you can use the fact here. Well, this is basically something from the table, that, well, integral of cotan squared theta plus 1 d theta is minus cotan theta. Okay, so using that fact, then we can write this into 2 pieces. One part will give us minus cotan theta. The other piece will give us minus 1, I believe, minus theta. And then go from pi over 6 to pi over 2. Okay, so, well, this is just applying the values then. Yes, minus cotan pi over 2 minus pi over 2 minus, evaluate the function in the lower limits, minus cotan of pi over 6 minus pi over 6. And what? Remember, a cotan of pi over 2 is 0. Cotan of pi over 6 is root 3. So you evaluate those ones and you find the value, the final value of your integral. Okay? One more example we have here. Root of integral of x minus 1 over root 8 minus 2x minus x squared. So when you look at this integral, you notice that, oh, the forms that we usually look for, a squared minus x squared, is not here. But if you note in the denominator, this is quadratic. It means that we can do complete square. So complete square in this specific case, 8 plus 2x minus x squared, we can write it as 8 plus 1 minus 1 plus 2x minus x squared. And if you look at the right hand side, this is 9. If I factor out 1, this will give me x squared minus 2x plus 1. And that's why it's called completing square, because now I have 9 minus x minus 1 squared. So what we found here is this is 9 minus x minus 1 squared dx. Why this is important? Now we can just do a simple u substitution, and this will give us what we are looking for. In the numerator we have u du over 9 minus u squared. And then you go ahead and set u this time equal to 3 sine squared theta, and that will give me 3, oh, not square, just sorry, sine theta. So 3 sine theta over root 9 minus 9 sine squared theta, then 3 cosine theta d theta there. And that will give us, well, this will generate, in the denominator we'll get 3 cosine theta, 3 cosine theta d theta. These two cancel each other, and what we left with is integral of 3 cosine theta, sine theta d theta, which is, the integral is negative 3 cosine theta plus c. Now you can use the fact that, okay, from here, the theta, this is u, this is 3, so the cosine will be u squared, or 9 squared, 3 squared minus u squared. So this I will do minus 3 root adjacent over hypotenuse. Okay, so that cancels with that. So we get 9 minus u squared plus c. And okay, well, this is turn back x values back there. So 9 minus x minus 1 squared plus c. And well, go ahead and expand that. That will give us the quadratic that we started with at the beginning. So it was plus 2x minus x squared plus c. Here you may have noticed that at this point, actually, let me put some. After that, we could have used the simple substitution, say t equals to 9 minus u squared. That would work as well. So this example shows that you can sometimes do easier in substitutions than trig substitution to get your integrals final answer, but I just continued the way that we had, and you can see that there are more than one ways to complete one integral. Okay, so these were the examples for a sine theta substitutions.